Hi, I'm Professor Goins, and welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in pretty much any college mathematics course, please consider subscribing and then checking out some playlists, watching some videos, liking, commenting, sharing those videos. Those are all really simple interactions that you can do, and any and all are greatly appreciated because it does help us to reach a larger audience and to ultimately grow, which we would like the chance to try to do. Let's go ahead and get into the current video. I want to take a look at the concept of homeomorphisms that you'll discuss in your topology course. Now, homeomorphisms play the role of, say, isomorphisms in a group theory course, where what I can do is I can show that two different structures are equivalent. Maybe they're basically just a difference of relabeling things. But basically, in algebra, if I've got one group that is, say, cyclic and another group that's isomorphic to it, then this one is also cyclic. Or if this one is finitely generated, then this one is finitely generated, so on and so forth, right? The idea is that if one group has a certain property, anything that's isomorphic to it would have the same property, and the same thing with homeomorphisms. If I've got one topological space that has a certain property, and I know that another space is homeomorphic to it, then this would have to have the exact same property. Or if I can prove something within this space, then the same notion applies to this other space. And essentially, before I kind of get into like the formal details, homeomorphisms are basically, if I have a topological space, what I can do is I can take that space and without ripping or tearing, if I can continuously sort of deform it into something else, then those two are topologically equivalent. Keep in mind, topologically equivalent and geometrically equivalent are very different things. Something that's geometrically equivalent would be topologically equivalent, but not in the other direction. Okay, so something that like a square and a circle, which I'll illustrate here shortly, are topologically equivalent. Another example is, let's take the following shape. So again, before I get into the formal discussion, let's look at the following shape. Let's take a donut or a bagel, right? So this is formally, you would call this a torus, but mathematicians like to call it a donut. Well, imagine I could take this, and if this was made out of like Play-Doh that didn't rip or crack or anything like that, but let's say it's some sort of like an elastic material, and I was sort of take this and start manipulating it so that I can kind of do the following. Well, maybe I was able to shift that hole, so maybe it starts to get over to here. I just kind of take some of this material and kind of like shift it over. So we still have this object that has a hole in it. And then what I'm going to do is I'm going to take that object and let's kind of start maybe squaring it off a little bit. So I still have this hole. Okay, so I still have this hole there. But this is still going to be some sort of a three-dimensional object that has a hole in the middle. And then what I could do, and let's sort of add some sort of a little bit more of a dimension to it here. Let's say it looks, again, so it's just maybe a plate or something with a hole in it. And then what I'm going to do is I'm going to, let's say I take my finger and I kind of push down into this. And so I start creating this cavity here. Okay, and I kind of start creating this cavity in this object. So this one has a hole, this is just a cavity. And then what I could do is I could keep making this cavity bigger, and I could keep making this hole bigger, and what I can create is something that looks like the following. A coffee mug. So what I can do is I can actually show topologically a donut and a coffee mug are equivalent. If I have a property of one of them, then it's equivalent to the other one has the exact same properties. Okay, so now that I've got this sort of like informal discussion out of the way, let's get into more of a formal discussion of homeomorphisms. So definition. Let's say I have a function f from x tau to y sigma. In other words, that's just a shorthand for saying f is a function, a set function from x to y, where x is the topology tau and y is the topology sigma. F is a homeomorphism if the following conditions are satisfied. F is continuous, bijective, and F inverse is continuous. Okay. In that case, then we also say that these two topological spaces are homeomorphic, and notation for that, depending on the textbook you're using, you might see different things, but here's one of them. If there's a homeomorphism between x tau and y sigma, we say that x tau is homeomorphic to y sigma, and we kind of give a notation like this. It kind of looks like just sort of like the approximately sign, equal to sign, but then I do a straight one on the bottom. But anyway, this is essentially an equivalence relation between topological spaces, and that's one of the things that the relation is homeomorphic to, is it provides an equivalence relation on the class of the category of topological spaces. Okay, and it's one of the most important topics or most important concepts in all of topology. Okay, so let me go ahead and take a look at some specific examples. Let's take the function f from 0, 1 to 0, 2, 3, given by f of x is equal to 3x. All right? Well, let's look at some properties of this function first. First and foremost, the function 3x is continuous. It's invertible. Right? It's bijective because 0, 1 to 3, 0, 3. If I plug in 0, I get 0. If I plug in 1, I get 3. It's a bijection between those. And it's also, its inverse, which would be x over 3, is continuous as well. And so therefore, this is a homeomorphism. All right? Any topological property that 0, 1 has, 0, 3 will have. Any topological property that 0, 3 has, 0, 1 has. Notice one thing that is not a topological property, and that would be length. The length of this interval is 0 to 1, the length of this interval is 0 to 3, but topologically those spaces are equivalent. Geometrically they are not, right? Geometric concepts like area, length, volume, those are not topological qualities, topological properties, and therefore they're not preserved by a homeomorphism. Okay, but these two topological spaces, using the usual topology, are actually equivalent. Next example. Let's take the function f from negative pi over 2 to pi over 2 to the entire real line, and let's say that the function is x is taken to the tangent of x. All right, let's look at some properties of this function. Well, first of all, the tangent function is continuous. It's invertible, right? Its inverse is tan inverse, and when I take the inverse, it goes from r to negative pi over 2 to pi over 2. So it's continuous, invertible, the inverse is continuous, and therefore this is a homeomorphism. Right? That means that, again, I'm using the usual topology. That means that the topological space between negative pi over 2 to pi over 2 and the entire real line topologically are equivalent. What this shows me is that boundedness is not a topological property. Clearly, this interval here is bounded, whereas R is not bounded. Okay? So boundedness is not a topological property. Another example. At the beginning of the video, I mentioned that a square and a circle are topologically equivalent. Well, let's take a look at the following. Let's take a look at a circle. All right. And let's take a look at the following square that I'm going to put inside. I'm just trying to pick which color would maybe stand out the best. Let's maybe do this one. Probably not the most accurate drawing here, but let's say I've got a square embedded inside of a circle. And let's just say for reference that this right here is the center of it. So what I have is, let's see what letters I use. X is going to be the topological space consisting of the circle, and Y is going to be the topological space consisting of the square. Now, let me show you why these are topologically equivalent. I'm going to define a function as follows. If I take a point, let's say I take the radius and I take one of these, say, radial segments here, I'm going to take this point right here and assign it to this point right here. So I'm going to take the point on the square and assign it to the point on the circle. First and foremost, you can see that that is a bijection. So not only is it injective, it's also surjective. So it is invertible. Okay, it does have an inverse. And second of all, if I take a point that's really, really close to this, so let's say I take from this point here, I go up just a little bit and I go to that one, and I was to define and look at the point on the circle corresponding to that. Essentially, the idea, it's continuous because the concept of closeness is preserved. If I take this point here and move it up just a little bit, then this point here moves up just a little bit as well. And that happens all around the circle, and it goes in both directions as well. Therefore, that function that I just defined is a homeomorphism. Okay, let's look at maybe certainly one more example. Maybe I'll do a second one, but let's see. Let's do one more for sure. Let's take the interval 0 to 2 pi, and this is not homeomorphic to the circle. All right. So the interval from 0 to 2 pi, that closed, bounded, and in particular compact interval, is not homeomorphic to the unit circle. Let's see why. Well, if I take the interval, let's say this is again 0 to 2 pi, and let's say over here I take the circle, okay, so this is S1, and let's say they were homeomorphic. All right, so let's say I did have a homeomorphism between those. Now, what we can show, and I'm not going to do it in this current video, but the idea is that if I have a homeomorphism between two topological spaces, for example, between the square and the circle, if I go back up here and I were to, let's say, remove, say, a point, it doesn't really matter where, but just for sake of discussion, let's say I remove these 2 points, then those two topological spaces, the circle with a point removed and the square with a point removed, those are still homeomorphic. Okay. Now, so therefore I could do the same thing down here. However, what happens? If I remove a point here, and then let's say I remove a point over here. All right. Well, let's see if there's any way to now distinguish topologically those two spaces. Now, remember that, so I'm basically just going to kind of let the cat out of the bag here, right? When we talked about the idea of connectedness, remember that the concept, if you haven't watched the video, take a look at it, but the idea is that connectedness is written in terms of the topology, therefore is a topological property. Meaning, if one space is connected, and then this is homeomorphic to it, both of these spaces have to be connected. Well, if I look at this, the circle, if I remove a point, this is still a connected space. If I take a point away, an interior point, in particular away. Now, if I take an endpoint away, it's still going to be connected, but it should work for any point. So if I take an interior point here, this is actually a disconnected space. There's a separation to this. But if they were homeomorphic, they'd still have to be homeomorphic after removing points. But this one and this one have different topological properties. Therefore, what I proposed to be a homeomorphism in the beginning, in fact, is not a homeomorphism. Therefore, these two are not homeomorphic. Okay. Thank you for watching, and please consider subscribing.